Okay, so last time we used Excel to find using both the corner checking method and the Excel solver method of finding the optimal choice. We had 1.8 slices of pizza and 3.3 games of Metal Slug. And I just want to demonstrate what was actually going on graphically, which is represented here. So the numbers are just slightly different, but you've got um, a time constraint and a money constraint. So you can see out there we've got 4 is the maximum amount of on one end and 6 on the other, and then 24 and 1.5. So we're constrained in terms of time and constrained in terms of times of money. Those two constraints form a feasible set here in the pink, where everything below one line is enough time, and everything to the left of the other line has enough money. So you get this shape that has where everything in that shape is feasible. So naturally, it makes sense that as we move toward the edges, we're doing more. So the optimal decision is probably going to be somewhere on the edge. But what's drawn there in pink is the isoprofit line. So an isoprofit line is a line that connects all the things that have the same value. So in our pizza Metal Slug problem, that line would have a slope of 4 because pizza is 4 times better than Metal Slug. That isoprofit line, we want to push it as far up and to the right as we can. And so you can see that corner checking is going to make sense because at the corners is where you have the chance to be furthest up and to the right. And notice that in this case, the upper right-hand corner was the best. But imagine if that pink dotted line was flat, left to right. Well, if it was flat left to right, the way we could move it up and to the right would be to put it right on 6. Right? If it was flat on 6, that would be as high if it was go. If it was vertical, we'd put it on 1.5 over here, and that would be as right as it could go. Because it's neither flat or vertical, it's at an angle, and it's at an angle such that it has a shallower slope than this and a steeper slope than this. We get here, that corner is the optimal solution. So we can only show graphically the optimal solutions to a linear programming problem when we have 2 variables and 2 constraints. So it's a pretty rare special case when this is true, but it's useful to see how it works. Okay, so we've arrived at a you try it. You are a supplier of injection molded plastic toys. And the profit per lot of 3 different types of toys is given below. So that's our profit. We want to maximize that profit given to our selection of the number of lots. We have a total production budget of $10,000, and we have a cost per lot. So notice that the first numbers are profit, so even though the profit numbers are smaller than the production costs, that's fine because the costs were the costs were included or factored in the profit numbers. So we want to stay under our production budget. That's going to be a constraint, and we have to stay under our time allotment for labor. So we have, for example, the vehicles use $3,400 of production per lot and 230 hours. So they are the most expensive, but the least complicated. So given these 2 constraints and that objective to maximize profit, find the optimal solution using Excel. So pause the video and give it a shot. Okay, the solution is posted there on the slides. Notice that we don't make any dolls. So the question is, how much cheaper would the dolls have to be in order to increase production just by a little bit? And the answer is quite a bit cheaper. You can verify for yourself, but it's not going to be worth doing the dolls until it's competitive with the other two options. And that means it has to become much cheaper. Alright, so let's start thinking about our specific classes of problems that we do. The first are transportation problems. In transportation problems, the objective is to minimize the distance. So we have our objective function is going to take our choice of what thing goes to what location, or the number of items or pounds or whatever our metric is to go from one location to another, and multiply that by the distance traveled. So in our pizza metal slug case, our choice was how much pizza and how much metal slug. In this case, we have how much of how much of sugar from Bobby is going to A, how much lemon juice from Bobby is going to A, how much sugar from Janice is going to A, how much lemon juice from Janice is going to A. So this is actually a much bigger problem if we think about all of the necessary inputs. I mean, a solution to this is going to tell how much of each item each person delivers to each location. So that's actually quite a big multiplication problem. 3 people times 2 inputs times 2 destination is 12 things. That's a big objective function. So if you look at how it would look, it's going to be we are going to have 1 times sugar times Bobby, like 1 times sugar Bobby A, and 1 times lemon Bobby A, and 6 times sugar Bobby B, and 6 times lemon Bobby B, and so on. So this is a common feature of these transportation problems, is you can label your decision variables by the different different factorial combinations that produce your set of outputs. So sugar Bobby A. So a final answer to this is I got 12 things I have to decide on. What are my 12 things that I'm choosing? What are the constraints? So if you look here, we're constrained in a couple ways. First, each only has 2 bags of sugar, and each only has 3 bottles of lemon juice. So we have to make sure we don't send more than that somewhere. And then we need 3 bags of sugar and 4 bottles of lemonade to make lemonade. So we have a supply constraint that we have to say under, and we have a demand constraint that we have to go over. This is common both transportation and assignment. So the difference when you're doing an HR type question is that the supply is always 1 per person, and the demand would be 1 per job. So if you're assigning people, it's like assigning sugar, it's just there's always only 1 bag or 1 thing. So how do we do that? So the constraints are, if we look at here, right? Let's go back and look at this. So Bobby can't send more lemons or more sugar, so that's 2. Janice can't send more lemons or sugar, that's 2. Susie can't send more lemons or sugar, that's 2. So we have 6 constraints there, and then we need A needs lemons and sugar, that's 2 more, and B needs lemons and sugar, that's 2 more. So if you look down here, our estimate of 10 was correct. We had 6 plus 4 is 10. But we can always add more if we need them. And you can do that in an iterative fashion if you look at what comes out of your process. So if we went through and solved this, we would find Bobby and Susie use all their supplies at the closest stand, and Janice picks up the slack at each stand, and the excess lemon juice was used to leave juice at Janice's house because she was the farthest one from both. So we've arrived at a you try it again. So we've got here 3 locations that are supplying product, Rose Street, Sparta, and St. Paul. And we have 3 locations that are demanding product on Alaska, the Village, and Goosetown. Notice, obviously, shipping from Rose Street is going to be better because it's close, but it only has 8. It can't supply everybody. So go ahead and see if you can think about how you might set that up, and we'll demonstrate a transportation problem in the next set of videos. But again, remember, an assignment problem, one with people and jobs, is just like a transportation problem, but you're maximizing skill instead of minimizing distance, and every supply location has a supply of 1, and every demand job has a demand of 1.